So we got two things by adding a leaky atmosphere, as we called it. It has a emissivity or a transmittivity or absorptivity. What does it mean? Basically, we're trying to get more realistic about the atmosphere, that it has a greenhouse effect, which means some of the energy from the surface can directly escape to space, but some is absorbed and then bounced back to the surface, which makes the surface warmer. Then the surface will emit more, and so on. So there is a feedback, and then there is an effective temperature that the atmosphere accomplishes, and it emits at that temperature to space, right? So that's a realistic situation because we actually have an atmosphere that's leaky to different wavelengths of the outgoing long wave radiation. To make it more realistic, obviously we have to consider that atmosphere is not only a single layer, but it's continuously stratified, as we will see soon, and each layer is absorbing different wavelengths and sending it downward and upward. And if you have two atmospheric layers, A and B, then A is emitting to space and B is emitting to the ground, and they are absorbing a part of it. So part of it is escaping from here to here and then to space. So could be different emissivities depending on various factors. And we are still showing here as if the shortwave radiation is coming all the way to the surface. Okay, so in other words, to be very realistic, we have to allow for shortwave to come in through multiple layers of the atmosphere, as we will soon see the real world radiation balance. That atmosphere is quite capable of absorbing a fraction of the shortwave as well, unlike the simple calculations we have done so far. And atmosphere is made up of many layers, not just one or two layers. So the net emissivity itself is also not going to come from just the top layer as we implied here. It can come from multiple layers because each layer is leaky. Okay, so you can quickly see how complicated things become. To put that in context, let's look at the average picture in the real world. We have 342 watts per meter squared of incoming solar radiation, which changes over time because of sunspots and very long time scales because of orbital changes and so on. But ignoring all that right now, let's say we have 342. And you can see that 77 of that is bounced back from various things in the atmosphere, like clouds. There are also scattering aerosols that can scatter solar radiation and have a cooling effect and so on. And the surface is reflecting about 30 watts per meter squared, so the net albedo is about 30%. Okay, close to 0.3. That's something important to remember, that the atmosphere is not really completely transparent to shortwave radiation. The net shortwave then that actually does the work in the at the surface is 168, because some of the shortwave is also absorbed by the atmosphere, not only reflected but actually also absorbed. So if you add 67, 168 and 107, you're going to end up with 342. That's the shortwave side of the story. The long wave side is even more complicated. So you take this 168 and 68 and you then do the balance to see that you send out the right amount of long wave, which has to be 342 minus 107, obviously, to balance at some long time scales. So you have 235 net short wave and then 235 net long wave. But the long wave has a lot of bouncing around in the system. The energy that's coming to the surface is going to produce thermals, which means heated air that rises from the surface, evapotranspiration, which is basically evaporation mediated by vegetation, for example, and there is the latent heat released by water that's been evaporated and is condensing in the atmosphere. That can heat the atmosphere, is in fact a huge contributor to the weather and climate, right? This is the main driver, as we will see later on. The surprising thing is, you will see the numbers here are much bigger than the total energy coming in, let alone the net energy. Net energy, we said, is 235. Here we have 390 watts per meter square. How did that happen? The best analogy is to think of yourself feeling cold and putting on a blanket. Why do you do that? Because you trap your own body's heat and warm the air inside by bouncing around the long wave that you're emitting, that the blanket can prevent from escaping, or the greenhouse gas, or the greenhouse for growing things, right, where a transparent structure allows sun's light to come in and prevents the heat from escaping and creates a microclimate that doesn't have all the heating and cooling outside, right? The same thing here. So you can generate a warmer body temperature by trapping your own heat. The same thing is happening here. So the key thing is to note here that 40 is out of the 390, 40 is escaping straight to space. This is the leaky atmosphere that we talked about. The rest is emitted by the atmosphere, by the clouds, by greenhouse gas effects, which are bouncing the energy back. You can see here 324 being bounced back by the greenhouse gases. So what is global warming? It's essentially the increase in greenhouse gas, which is going to increase this energy that's bouncing back to the surface and warming the surface and the atmosphere, right? So it's absorbing more of it, warming the atmosphere obviously, and putting a lot of the energy into the ocean and warming the surface. Okay, so obviously real life is complicated, but the basic ideas you have of balancing incoming shortwave, worrying about albedo, the leaky atmosphere, etc., they are all solid concepts. But the additional complication is that the energy going out to space is not just from one layer, right? As you can see here, there is some going from the clouds, from directly from the atmosphere, some directly from the surface, and so on. So the debate about exactly how the energy balance is happening in the global warming is also not complete. Yes, even in 2020 there are many questions to be answered. And one of the ideas here, I took the animation from one of the papers you can Google for, bases itself on the fact that the atmospheric temperature profile itself shifts and the layer which is emitting to space is getting thicker. In some sense, you can see here that the energy is going from multiple layers and from multiple layers that are changing their temperature with increased greenhouse gases. So radiative transfer is a complicated calculation, a very complicated calculation in fact.